All right, good morning, everyone. It's cold out there today. So today is one of the most important days in the semester in terms of what we're learning, because we're going to learn one of the most fundamental ideas in machine learning, which is the idea about generalization and the bias variance trade-off. So just to remember where we were last time, we were setting up a model which could provide us with this analysis. It's a relatively simple model. There's many more complicated models, but for the kind of regression we're doing, this is all we need. And just to highlight a few things about this, so this is the first time that we have seen random variables in this course. So let's just talk for a second about what a random variable is. So a random variable, we can think about it as really almost like a function that generates things. So if you want to think about a coin is something you can flip many times, and every time you flip it, you get a different number out. But there's, depending on whether the coin is fair or unfair, you're going to get a certain distribution of heads and tails. And that coin itself is like the random variable. It's something that can generate all those examples. And it has some statistics associated with it. Here, this thing epsilon, this is not a binary random variable. This is a real number. If you want, you can think about it as this giant bag where every time you put your hand in, you pull out a number. And every time you pull out real numbers, and they're going to be different every time. But those numbers that you're pulling out, they tend to have certain properties. Like this particular one has a mean of 0. So that means that if you look on average about the numbers you're pulling out, they tend to average around 0, and the variance is sigma squared. So the size of the numbers, their average squared value is sigma squared, and so on. So that's the idea. We're finally dealing with random variables. Until now, we haven't needed to do this, but now we do. So when we have these random variables, we have these operations. The most fundamental one is expectation. So we have a slide here on expectation. So the expectation, this is this thing with the fancy E. Here, this is the mean or the average value of a random variable. So again, if we don't have a random variable, this concept does not apply. So this is special to random variables. On this page and the next, all the random variables will be capital letters, and the deterministic ones will be small letters. So how do we mathematically define this, this expectation? So if we have a random variable, capital A, that generates real numbers, one of the ways that we can describe everything about that random variable is through its probability density function. In Spirit, it's like a histogram where you get to see all the different possibilities and how frequently they occur. But a histogram is something that we generate from a finite number of data. It has a finite number of bins, where this probability density function is often a smooth thing, and it represents the random variable itself. Tells us the frequency of all the different things the random variable could generate. So if you have this probability density function, we'll call it P sub A. The subscript A tells us that it's about the random variable, and then the argument of it, so this is for let's say for a Gaussian one, the PDF of a Gaussian, zero mean Gaussian would look like this. So this would be A here. This is PA as a function of A. And this would tell us that the values near 0 are more probable than the values away from 0. And as you get far away from 0, the probability decays very quickly. So that's what this picture would tell us. Okay, so given that, if I want to compute the average value or the expected value of some function of this random variable a, and it can be any function, then this is the expression we have. This is what we mean. You have an integral. You take that over, in this case, the whole real line, because the random variable outputs things in the whole real line. You have the probability density function here, and then you have the function f of a. So the little a here is just the dummy variable. It's just the variable of integration. Here, it's another dummy variable. It just tells you where you are along the line, where you want to look at the density. And so when we take the expectation of a function of a, this is what we're doing. Let's think about a simple case. What if I would just want the expectation of a itself? That means that the function is a trivial function that does nothing. In that case, I have expectation of a, and I have just a here. Okay, so that would be the expectation of a. But you can generalize this. If you want to take the expectation of a squared, that's f is the squaring function, and here you would have a squared, and here you would have a squared. Okay, so this is a general concept for any function of a random variable a. Any questions on this definition? Okay. Have you seen this before? Okay, good. Hopefully you've seen this before. Maybe it's a while. Maybe you feel like you never learned it well enough, but the more you use this stuff, the more it makes sense. So this is for a scalar valued random variable. You can also do this with a vector of random variables. You just need a different, scalar integral for every one of the variables in the vector. Okay, so even though this is the definition, we're not really going to use this definition very much. It's good to know about it. We're going to use two important properties of the expectation very frequently. So in stating these properties, let's think of capital A and capital B as the random variables. And let's think of these f and g as arbitrary functions. And let's think of the little small lowercase letters c and d as deterministic variables. So the first key property is linearity. Okay, so it goes like this. So if we have the expected value of c plus d times some function of a, then the key point is that expectation is a linear operator. So the expectation, we can apply it individually to these two terms that are added together. And in fact, because d is just a scaling term that's not random, the d itself can come out of the expectation and we get this. Okay, so this is probably what you remember from a signals and systems course about a linear operator applying on something of this form where you have a scalar plus scalar times a signal. The linear operator works in the same way as this expectation. So hopefully this linearity concept is familiar as well. Any questions on this? Yes?
So the expected value of a scalar is just scalar?
Exactly. Yeah. Just for intuition, think of expected value as average. The difference between the statistical average and the sample average, in a sample average, I have a list of numbers and I just average them together. Statistical average, I have a random variable and I have to think about all the possible, often infinite number of things that can happen with it, and I average those things together. But they're both averages. Okay. Good question. Any other questions about random variables or this linearity property of expectation? Okay, so we'll be using this a lot. Now notice that I could not move the expectation through the function, or I can't pull the function out because this function may not be linear. This might be like the squaring function. So that's why I have to stop where I stopped here. Okay, next property. What if I have the expected value of a product, f function, some function times a, and another function g times b? So the question is whether I can split this into the expectation of FA times the expectation of GB. Does this expectation split? And the answer is it does, but only if these random variables A and B are what we call statistically independent. So for independent random variables, we can split the expectation, otherwise we cannot. And what we mean by independent, statistically independent, is that if you look at the joint probability density function of A and B together, that this can be factored as the probability density function of A times the probability density function of B. And in fact, it's not too hard to prove both of these properties from this basic definition. So, but these two properties are things that we want to just get used to because these things show up a lot. Any questions on this second independence property? Okay. And like I mentioned last time, I wrote a short document that tries to explain all this just from very basics, what are random variables, what's expectation, all this stuff. And you can find this on the course Git repo. Okay. So any other questions on expectation? Okay. Let's move on to a related topic called conditional expectation. So conditional expectation, you have the expected value of something, let's say function of A, given another random variable B. So in words, what we're doing is this is the mean value of a function f, a random variable A, given a fixed value of some other random variable B. So let me give you an example. If I said, what is the temperature at noon in Columbus, Ohio? And I'm not telling you what day of the year it is. You have to answer that question by thinking, well, it might be January, February, March, and then you're going to get the average temperature on any day of the year, and that might be 60 degrees or whatever it is. But now if I said, what is the average temperature given that it's January? That's a very different number, right? Now you have this information, oh, it's January. So given that, the temperature is related to the month, and now I'm going to have a different average temperature given that it's January. Maybe it's going to be 20 degrees instead of 60. So if I condition on that extra piece of information, which is the month of January, then the temperature changes quite a bit. So that's the idea behind conditional expectation. If these two random variables are statistically independent, if B and A are statistically independent, the conditioning does nothing for us. But if there's some probabilistic link between them, then the expectation of FA is going to be generally different than the expectation of FA given B. So we refer to this as given B. Okay. All right. So any questions on just the main idea? Okay, let's take a look at the mathematical definition. So here's the definition, and it looks very similar to before. The only difference, actually, is that instead of plugging in the probability distribution PA, we're plugging in this conditional probability distribution PA given B. And this conditional distribution says, what is the distribution of A given, or the probability density of A, given that random variable B takes on the specific value little b. So that's what's changing here, is just this part is the only thing changing. The first part, f of A, in this expectation is the same. Okay, so notice another thing here. I'm conditioning on the specific event that random variable B takes on a specific value little b. Okay, so the reason that we care about this is that one of our main quantities of analysis is the mean squared error on the variable y hat. You know, how much does y hat differ from the true y? Given a certain test feature vector x. And so that's where we get, sorry, let me try to clean this up. This is where we get this conditional and conditional mean here. We're saying for a given test vector x, given that test vector x, what is the mean squared error on y hat? And as we'll see through some nice pictures, this can change quite a bit depending on what x is. Okay. Good. Any questions on this? Okay. A related concept that you'll sometimes see is what we call the law of total expectation. So this talks about what happens when you have a conditional expectation and then you take another expectation over that. So let's think about this conditional expectation for a moment. So is this, actually let's go back. Let's talk about this expectation. Is this a random quantity or is this a deterministic quantity when I actually take that expectation? Is deterministic. So A is random. The function of A is going to be random. But once I say what the average value of that random vector is, that average value is just a fixed deterministic number. Okay, so this is deterministic. What about this, though? So it turns out that this thing, this is a function of B. B is a random variable. So that means that this whole thing is random. So when you keep that in mind, this whole thing is a function of random B. When I take this one additional expectation, then I'm averaging over B. And now the result is no longer random. And in fact, the result is just the expectation of A. Let me try to describe this with an example, the temperature example. So this is like, what is the temperature at noon given that the month is B? Well, if you want an actual number, I have to tell you exactly what month I'm talking about. That would be like fixing B at some value. But if I don't do that, then this temperature is just a function of the month. And so now if I ask you, what is the average over all months? What's the temperature given a particular month, but now averaged over all months? We just get back to the average temperature. So this thing is called the law of total expectation, but it shows up pretty often in our derivations. And so it's just good to know about. Okay. Yeah.
Could you go over that again?
Sure. So, okay. So let's start here. Let's say this is the average temperature given that the month is January. So that would be like I'm fixing January. If I didn't fix this, little b, and I just said the average temperature given the month, then this is still a function of the month. I haven't told you what the month is. And the month is maybe some random, I'm treating it as a random quantity. Maybe I'm thinking that the month is just uniformly sampled January or February, each with probability 1/12. But at least here, I'm not telling you the specific month I'm talking about, so it remains a function of month, and month is random. So, this expectation is just a random number, but it's still a function of this month B. So I mean, I could even write this formally over here, I could say this equals G of B for some G and for some G. There's some function G that I could write this as G. And they both share this dependence on B, which is random. And so as a result, they're both just some new random variable. The point is, if I take one more expectation of this quantity GB, I get back to the expectation of A. I believe that I gave a short proof of this in this handout. It's not difficult to prove. Yeah. We can always think about expectation as removing randomness. So this inner expectation is we're removing the randomness caused by A, but we're fixing B. And so B is still random, so this whole inner expectation is random. But the only randomness that is caused here is due to B. In the outer expectation, we're removing the randomness due to B. And now the result is no longer random. Okay, any other questions? Some of this stuff, the more often you see it used, the more natural and intuitive it all becomes. Okay, so let's again just, armed with that, let's come back to our model and think about our model again. So we're saying that we have a model. This model up here, this is the same model is going to apply to the test and the training data. We're going to have some feature vector that's going to be acted on by some function to produce what we would call a noiseless target, but then we're going to add noise to get our actual noisy targets. This function might be a polynomial, it might be linear, it could be anything really. It's not important to us. This random noise we're adding, we want this to be zero mean, means on average, epsilon takes a value 0, and have a variance of sigma squared. And we want that every time we use this model, so if I use this n times to make n training samples, every time I use this model, I want this noise to be independent of all the other times I used it. So the noise is independent over the draws of this random variable. As we discussed, this fancy E is expectation, and that's the true model. So this is the true model. That's how the data is actually generated. Now, we, as data scientists, we don't know the true model. Nature doesn't tell us the true model. We have to guess. So we're going to guess some model. We might guess well or we might guess poorly, but we're going to use f hat. And as is common in machine learning, our model is a function of a bunch of coefficients, beta, that we must learn. We must set them. And the way that we set them is we're given access to n samples of training data. And we learned, a good way of doing this with multiple linear regression. We know, given this training data and given a model f hat that we can use for multiple linear regression, we know how to find those coefficients beta hat. But let's remember that we should think about this training data as random. When I do this experiment once, I get one set of x and y's. But I might do this experiment again and again and again. Every time I do it, I'm going to have a different set of x and y's. So I'm thinking of the x and y's themselves as random. Some of the randomness comes from the fact that the y's have this noise in them. There may also be randomness in the xi's. So those are the sources of randomness in the training data. And because my beta hat is directly dependent on my training data, beta hat inherits that randomness. So these are random variables. Okay. For my analysis, though, I'm going to treat x, the test feature vector, I'm going to treat that as deterministic, and we'll see why. Because I want to test what happens when x is this value and this value and this value. I want to see what happens as I change x. So I'm going to treat x as deterministic. But I do need to make sure that my test error, epsilon, is independent of however I choose x, and thus it will be independent of beta hat as well. And finally, the analysis we want to do is we want to derive an expression for this mean squared error given this model, which is very similar to normalized RSS. It's just the statistical, let me write that down. This is like the statistical version of RSS over n. I'll actually write here test RSS over n test, where I have n test samples and I'm averaging what happens. And I want n test to get very large. So as n test grows to infinity, it turns out by this thing called the law of large numbers that this quantity will converge to this MSE. I don't want to make it complicated. I just want to provide a connection between this mean squared error and the stuff we were doing before. Okay, so are there any questions on the model? All right, so we have everything we need now to do the derivation. We know the model, we know about expectation, and we can finally do this analysis, which will give us one of the most important equations for the whole semester. And this is called the bias variance formula. So we start with mean squared error. Okay, this is what we want to analyze. This is the mean squared error on y given x. And by definition, this is what it is. So the next step is to plug in our expression for y, the true y. For the true model, we know that this is the true f as a function of x plus epsilon. Second, we have to plug in our equation for y hat. That is the hypothesized model as a function of f using the training features, the coefficients beta hat that we learned from the training data. And notice that this is a conditional expectation. So I apologize for the late update, but in the previous version of the notes, I was trying to do something which made things a little less crowded here, but I realized that it could be confusing. So what I did in many of the notes you're looking at is I removed some of these conditioned on x's throughout. I just said, pretend, I said we're going to remove them, but they're there. And I think that can be confusing. If I don't want to give you guys the impression that this thing can just be taken away, because it has meaning. And if you remove it, you're actually talking about a different quantity. Okay, so on this slide, I have the given x. Everywhere there's an expectation, there's a given x. Okay, and I just uploaded these to the Git repo too. So this version of the slides. Okay, so we have the definition. We plugged in the equations for y and y hat. Now we just have to do a little bit of work, and we can use our knowledge of expectation to simplify things. So the first thing is we have a quadratic here. We're going to think about this as a quadratic of a sum of two terms, and we're going to expand this quadratic. So we're going to have the first term, epsilon squared, and then we're going to have the last term squared, and then we're going to have the cross term, 2 epsilon times the f stuff. Okay, so I'm just expanding the quadratic. Next, I'm going to use the linearity property of expectation and the independence property of expectation. And in particular, what I'm going to exploit with independence is I'm going to exploit the fact that the test error, epsilon, is independent of the training quantities, beta hat. Because beta hat is random because of the randomness in the training data. Epsilon is purely test data, and we know test and training data are statistically independent, conditioned on, the model and all that stuff. But so that independence allows me, okay, so first of all, linearity. Linearity allows me to say expectation of a sum of three things is the sum of the expectation of the first plus the expectation of the second plus the expectation of the third. So that's how we can use linearity. But now what I did with the expectation of the second, which is the expectation of this thing, I split it into the expectation of this times the expectation of this. So this is where I use the independence, because epsilon, okay, first of all, x is deterministic, it's not random. So the only randomness here is coming from beta hat, and I know that beta hat is independent of epsilon, so that means I can split this into expectation of this times expectation of this, and that's what we have here. Okay, the two is obviously not random, so I can pull that out of the expectation. Okay, any questions about that splitting? Okay, independence. Now, I can look at this. What's the expected value of epsilon given x? Okay, so the first thing to remember here is that since x is deterministic, because epsilon is statistically unrelated to x, this is the same thing as the expectation of epsilon. X is not affecting epsilon at all. So conditioning on it, we can just remove that without worrying about it. So finally, I have expectation of epsilon. What is the mean of epsilon? We said that's 0. So that means that this first term goes to 0, and therefore 0 times this is 0. So the whole thing goes away, leaving me with the first and the last terms. Any questions on that? Okay, so now this last term, we're going to have to be a little clever. What we're going to do is we're going to sneak in a quantity that equals 0. So here I have minus some expectation plus the same thing, right? So that whole thing is 0, so I can obviously put 0 in there. But the reason I'm doing this is that it's going to make my life a little bit easier going forward. In particular, what I'm going to do is I'm going to expand this quadratic, and I'm going to think about this as a sum of this plus this. And so when I expand this quadratic, I'm going to have the first term squared plus the second term squared plus the cross terms. So let's look at each piece on its own. So the first term, squared. Okay, so first of all, so this is the first term squared. There's, what do we want to say about this? What we can say about this is, okay, f of x is deterministic in the sense that I'm conditioning on x, so I'm not thinking of x as random. So this is deterministic. This, as an expectation, is also deterministic. So as a result, this whole thing is deterministic, which means that this expectation does nothing. So I can remove the expectation. I'm taking the expectation of a deterministic quantity, which is just that quantity. So we can do that. Is everybody with me there? Okay. Let's think about the next term over here. This term actually, yeah, we're actually not going to do anything with this term at all. We're going to leave it. Let's focus on the third term. This is the cross term. So, so first of all, we removed, when we did, let's see, when we multiplied this times this, and we had the expectation on the outside, what we did is we pulled this out because this whole thing is deterministic. So by linearity, we can just pull it through the expectation. It's just like a scaling function on the outside. So now the expectation is just applied to what remains, which is this. And let's think about this. There's a couple ways to think about it. One way is that I have something minus its mean. That must be a zero mean quantity. If I subtract the mean from something, it becomes zero mean. And then if I take the average of a zero mean quantity, it goes to zero. So that's one way of thinking why this thing goes to zero. Another way of thinking about it is, imagine that I just want to use the linearity property and I distribute this expectation across here. So I'm going to get expected value of a deterministic quantity is just that quantity on its own, minus expected value of this. And those two terms are equal, so when they subtract, they vanish. So there's two ways to think about why this goes to zero, but it does, and as a result, this whole term there disappears. Is this making sense, or can I answer any questions about that? Okay, so after all this, we finally get the, there was one thing I never explained, which is this. Okay, so here, as we said before, x is statistically, or epsilon is independent of x, so I can remove this. I can remove this expectation. It's not doing anything. Sorry, the conditioning is not doing anything. And I finally get what is the expected value of epsilon squared, and we said before that that was sigma squared. So that's where that came from. So after all this then, we have mean squared error is a sum of three terms. Each one has a special meaning. The first one is what we call the irreducible error. This is just the fact that if I'm trying to predict these y's, and these y's are corrupted with an error that is independent of everything else, there's no way I can ever figure out that, and I will always get a penalty. The noise of that will always affect my estimation. And so that I just get, even if I have a perfect model, even if this exactly equals f, I'm going to have epsilon left over, and I'm going to have a mean squared error of sigma squared at the minimum. So that is where this irreducible error is coming from. Okay, next, we have this term here. So we have a quantity which we call the bias that gets squared. I'll talk about the bias in a moment. The very last quantity is this, and all we've done is we've just swapped these two things. Because it's squared, we can subtract one from the other or the other from the one, it doesn't matter. And so finally we get this last term that's the variance. So the MSE is this irreducible error plus the bias squared plus the variance. And let's talk more about the bias and variance. So the bias looks at the difference between the true noiseless model and the average. Now here the average is the expectation is being applied to the training coefficients. The average prediction. So think about it this way. If I run one experiment and I get one beta hat vector and I make one f hat prediction, it's not going to be perfect. And when I do this again, I do another experiment with another set of training data and I get another beta hat vector, it's not going to be perfect. But maybe if I do this over and over and over again, on average, these ones agree with this. In that case, we would say it's unbiased. So on average, it's doing the right thing. From one experiment to another, there's a little error, sometimes less, sometimes greater than 0, but on average, it's 0. I'll show you some pictures that I think will help to visualize what's going on. But this is the bias. The last quantity is trying to look at, notice that the true model occurs in this expression, but the true model doesn't occur at all here. This is all about the predicted model, and it says, how much does the predicted model deviate from its average? So the more variation you get in the predictions around its average, the larger this variance gets. This is the average squared of this difference. And when you think about the definition of variance, like we saw sample variance, but statistical variance is similar, you always look at the average of something minus its mean squared. So that's why we're saying this is the variance. And in fact, this thing is y hat. So that's why we say that this is the variance on y hat as a function of x. So as my test features change, this variance quantity can itself change, and I'll show you some pictures. Similarly over here, as x changes, the bias on y hat can change. Okay, so a lot of math on this slide. We're almost ready for a visualization that I think will tie everything together. Before I do that, though, just one more concept is that so far we've been fixing the test feature vector x. So this equation that we derive down here is all about what happens at a specific test feature vector x. Now you might say, I don't really care about any specific test feature vector x. I want to know what happens over some distribution of, x's that I'm going to see in the future. And if that's the case, then you think of x as random, and you take one more expectation over that random x. And now you get a quantity which no longer depends on any particular x. It's just the average test error over this big test data set. And so finally, you're going to get the irreducible error times the average of this squared bias times the average of the variance, where again, these averages, these expectations are taken over the random data. And we'll use this in the future. But this is finally going to give us just a plain mean squared error that does not depend on anything, just the average mean squared error. Okay. All right, any questions on the derivation before we try to make sense of it with some pictures? Okay. So I think these pictures are really helpful in explaining all these ideas. So we're coming back to our polynomial demo. So remember that in our polynomial demo, we had this noiseless true model, which was this third order polynomial, which is given by that red curve. And if you remember, our data points in a particular experiment, our data points were just, noisy above and below that model. So that's what they looked like. So let me just clean that up. Okay, so let's say that I start by estimating or hypothesizing a linear model for my f hat. Now, as we know, a linear model is not going to do the right thing for a true model that's polynomial. And so what I'm going to plot now is two things. When you look at the solid green curves or line here, the solid green curve is going to be the mean of y hat over 100 different training experiments. So 100 different times, I'm going to make a training data set. I'm going to fit a least squares model, and then I'm going to make predictions. And when I make a prediction, it's actually going to be, this is my deterministic x along this axis. So I'm going to make a prediction for this x, and then this x, and then this x, and this x, and that's why I'm treating x as deterministic. For every x, I can make a prediction based on the coefficients I trained. So I'm going to do this 100 times, 100 different experiments. Every time, I'm going to get a different set of y's. So finally, I'm going to plot a mean over all those y hats. And that gives me this solid green line. Second, I want to know how much variation I have across those 100 experiments. So I'm going to plot these error bars. These error bars are going to be plus minus 1 standard deviation of y hat over those 100 training experiments. And of course, the variance is the standard deviation squared. So let's focus on this first picture. So because we have a linear model, every time I run an experiment, I'm going to get a line. But because my training data is always varying, that line is going to have a slightly different slope and a slightly different offset every time, right? For every experiment out of the 100, I'm going to have a slightly different line. So what I'm showing you here, this is the average of all those lines. That's what this green line is showing. And these little error bars are quantifying how much variation I had among all those lines, among all those experiments. As you can see, there is a bit of variation. As you get to the outside, the variation is larger than the inside. That makes sense because if I have lines like this, you can see there's more variation here than there is in the center. So everything is making sense. Now in this case, if you ask the question, is my model doing the right thing on average? If it was doing the right thing on average, this green curve would be matching the red curve. Obviously, it's not doing the right thing on average, although I guess it is for certain x. Like for this x, it's doing the right thing on average. For this x, it's doing the right thing on average, and so on. But for all these x, it's not. Right? So you could say that it's unbiased here, and it's biased everywhere else, which is look at the gap between the true noiseless model and the average of my predicted models. Okay, so we would say that this has a lot of bias in general. But if you look at the error bars are pretty small, so you could say it's pretty low variance. Let's look at another case. What if I choose d equals 3, and remember d equals 3 happens to be the true model order. And now I redo this. I do 100 experiments where I train my beta hats, and I'm going to get 100 different curves, but I'm going to look at the average curve, and I'm going to plot that as this solid green line. And what's cool is that you see that the average matches the truth exactly. So this shows we have no bias. So it's doing the right thing on average. Now that doesn't mean that my predictions are always perfect. In fact, my predictions are probably always imperfect. They're varying a little bit. And how much they vary, depends on the experiment out of the 100 that I did. But if I look at the average standard deviation, I can plot to see how much variation I'm getting. And the variation is, so the variance has increased. So if you look at the size of the error bars here and the size of the error bars here, they got bigger. So as my model got more complex, my variance increased. Let's go one step further. What if I overestimate my model, and now I have a 14-order polynomial model? The true model is 3. So that means it is possible for me to find a beta hat vector that matches the true beta hat exactly. I would do that by setting the first 3 coefficients non-zero, and then all the other beta hats, I would have to set them 0. And if I did that, I would be perfectly getting this model. It seems like that's what's happening on average, but it's definitely not happening every experiment. So when we look here, we see, again, it's unbiased. It's doing the right thing on average because there's no gap between the green and red curves. However, the variance got a lot bigger. The variance increased again. Look at how big it is over here now. So this is a general trend that you see. As you increase your model complexity, your bias tends to go down. You can do a better job on average, but your variance tends to increase. And that's exactly what we see from these experiments with this polynomial demo. Okay, so this is a great time for questions because there's a lot of ideas here. Are these plots making sense? Yes.
So is variance a random error?
Variance, by definition, what is variance? Variance is the difference in the predicted model from its average. So I would not say error because to me, error you have to compare to the truth. We're not actually comparing to the truth. We're just saying how much variation do I see in my measurements, or my prediction do I have from one experiment to another. So that is what's increasing as our model gets more complex. As our model gets more complex, we have a better chance that we can fit the truth. When our model is too simple, there's no way we can fit the truth because the truth is doing something complex, we're doing something simple, we're always going to have an error here. But as our model gets more complex, eventually, in some cases, it can perfectly fit the truth, and then this will go to 0. On average, our model is fitting the truth. Now, it's not doing on every realization, it's just happening on average. So yeah, let me just highlight irreducible error, bias, variance. So these are the important quantities that we derive. Okay, some more questions, like are these pictures making sense, what we're showing here? Okay, just remember this is all a function of x, and that's part of the reason why we're thinking about x as deterministic, so that we can sweep x and we can ask questions about the bias, is there a gap or not? And then we can ask about the variance. So as you can see, the variance here was larger here than here. Here, for some reason, the variance is larger here, I think. It could be an optical illusion, but the variance does seem to be, changing a little bit as you move through this x. All right. Yes?
So, for example, are we looking for a lower bias or a lower variance?
Great question. We want the lowest mean squared error. So it turns out that we have a trade-off. This is exactly the next thing to talk about. We want to do some combination of minimizing both of these. If we make our model too simple, this will be huge, this will be tiny. If we make our model too complex, bias will be tiny, variance will be huge. We want to do something in the middle where we make the sum as small as possible. Yeah. So that actually is, let me just skip a slide, skip ahead. This is exactly the idea behind the bias variance trade-off. Generally speaking, you can't get everything you want. So as this picture, this is just kind of a prototypical picture. So if I have and this is versus model complexity. So if I have a really simple model over here, then my bias, squared bias, is very large, but my variance is small. The sum of these plus the irreducible error gives me my mean squared error, and that's very high. Now if I go over here, I have a very complex model, squared bias is very small, but the variance is very large. Once again, my mean squared error is large. So I want to come somewhere in here, I get a good trade-off. Neither of those are as small as they could be, but somehow they're making a good compromise, each of them, to get my overall mean squared error as low as possible. So some of the terminology from before, as we go to the left, that's what we call underfitting. As we go to the right, that's what we call overfitting. We want to be right in the middle. We want to be neither underfitting nor overfitting if possible. Simpler models to the left, richer, more complex models to the right. Yep. So this is something we have seen, in the context of mean squared error with linear regression, polynomial regression, and so on. It actually holds a lot more generally as well, but for us, this is enough to really show the main concept. Okay. Any other questions on bias variance trade-off, or coming back to these pictures? Okay, so just one last thing here. Let's focus on this particular problem of least squares linear regression, and let's say that the true model has a certain number of betas. Let's call it the true number of beta d true, and let's say that our estimated model has some other d that may be smaller than d true and may be larger than d true somewhere. And we would like to know, and there's one other thing too. We have exactly n training samples. We would like to know the performance of our prediction as I change d and as I change n. So here's like 4 kind of main results. This is all derived in a handout. You can look at the derivation. But the first result is, we saw this before, if you have too few training samples, if the number of training samples is less than d plus 1, you get this non-invertible matrix, and there's actually no unique least square solutions. There's many least square solutions. We can't even really talk about things when our training data is not enough. So that's not a very interesting thing. What if our model that we choose is too simple? It has less coefficients than d true. Then you can show that your prediction will always be biased. So if d is less than d true, be biased. On the other hand, let's assume that I choose my d greater or equal to the true one, and let's assume that I have enough data so that this non-uniqueness problem vanishes. Then the cool thing is you can prove that y hat is going to be unbiased. And in terms of definitions of what we mean by unbiased, there's two different ways to say it. You can say it as the expected value of y hat minus y given x is 0. This is for all x. Or you can say it in terms of the expected value of f hat given x is fx. Equivalent ways. So the final thing is very interesting. Let's assume that I'm in this unbiased regime, so I have a model that's capable enough, and let's also assume that the number of training samples is very large, much greater than d. And finally, let's assume that my test features have the same distribution as my training features. In this case, you can derive that the variance on average, I'm taking my average over x, is d plus 1 divided by n times sigma squared. This tells you exactly why we want large data sets in machine learning, why we don't want small data sets, because as the size of the data set n increases, you can see your variance decreases proportionally. You can also see the problem with having too many features. If you use a model that has too many features, it's directly reflected in your variance. It will increase proportional to the number of features you use. And this is all magnified by this variance of the error here. So this is a really cool equation that just summarizes a lot of the concepts we saw before in pictures and everything. Variance is increasing linearly with number of model parameters and decreasing inversely with number of training samples. So this is a very powerful motivator for big data and not making your model too complex. So that's, I believe that's, there's one more thing. I'll save that for next time. And next time I'm also going to just quickly go through some of those handouts I've been talking about so that you see a little bit about what's in them. Okay, see you guys on Friday.